Hi, I'm Meta Spencer. Actually, there already is a solution to global warming. It's called cloud brightening. And today we're going to talk to two people who understand how to do it. One of them is Professor Stephen Salter at the University of Edinburgh. And then let's go to England, to the University of Leeds, where Alan Gadian is. Is that how you pronounce your name, Alan?
That's right. Thank you. Thank you.
Good to meet you. You are a modeler, and we're going to have a conversation about what you found out with your modeling, right?
Thank you. Yes.
Glasgow has come and gone, and people have been there and have returned home. As far as I know, there's almost no conversation about brightening the clouds. And to me, that is tragic. Hi, Stephen. Tell us about cloud brightening and why that's something we should be getting ready to do.
Okay. A present problem is because we're retaining too much of the heat from the sun, and the amount we're retaining is about 1.7 watts per square meter, and that is what we've got to not have sometime in the future. Now
hold on, let me let that sink in. 1.7 watts per square meter.
Yeah.
Okay. Now, if I have a light bulb, all I can transfer that to logically is a light bulb, which has like 100 watts.
Yeah.
Okay. Now, so one or like almost 2% of the light bulb per square meter on the planet is excess.
Yep.
Excess. So it's not how much we're the total, but it's the excess amount.
That's what we don't want to have.
Yeah. Retain it.
Now,
okay.
The amount of solar energy coming in on average over the whole surface is 340 watts per square meter, which is very conveniently just 200 times more than we don't want. Okay. Now that's
so now hold on. Let try to get. I'm really going to try to understand this today. 304. It's like having a light bulb shining 340 watt light bulb per square meter. Yeah. Is that is in the middle of the day or?
No, that's averaged over 24 hours.
Over 24 hours. So during the brightness of the day, it's a lot more than 300. Okay, got it.
Into the top of the atmosphere, it's 1360 per square meter, but we're losing a bit coming through the air and so on.
Okay.
Can I just interject here and say, if you think of a 100-watt light bulb, then 1 watt per meter squared is the radiation you receive about 3 yards away, about 3 meters away. So if you're 3 meters away from the light bulb or 3 yards away from the light bulb, 1 watt per meter squared is what you will get on your hand at a distance of 3 yards or 3 meters from it.
Yeah, that's because it's going to reflect and bounce around.
No, it's going to spread out.
Right.
So it's going to spread out in all directions. So the radiation reaching your hand there, 3 yards away, 3 meters away from the light, is about 1 watt per meter square.
Okay, now, but that would vary if the light is landing on a black
how much is absorbed
as opposed to white.
Yeah.
Okay, got it.
Sorry to interrupt, Steve.
What this means is that if we could reflect about 0.5% more of what's coming in, just 0.5%, we would cancel the problem. All right. And the clouds are reflecting somewhere between 25 and 75%, okay, on their own, according to different conditions. So we only want to change a tiny we only want a tiny change of reflectivity of the clouds to fix the problem. Okay. Now, we haven't got clouds everywhere, and the way we want to do it is only over the sea, and we haven't got the right kind of clouds over all of the sea. So we probably would like to increase the reflectivity of some of the clouds by about 5%, all right, rather than 0.5%. And a chap called Sean Toomey did a lot of work on clouds. He could fly over them and measure heat coming down, the energy coming down from above, and how much was coming back up from the clouds below. And he could also fly into the clouds and count how many cloud drops there were in a cubic centimeter and how big they were and so on. And he showed that the reflectivity of a cloud depends on the size distribution of the drops, and a large number of small drops reflects more than a smaller number of bigger drops, but the same amount of water. And you knew that already because you've heard people say the dark storm clouds are gathering.
When I see black clouds, that means that there's someplace over there are droplets forming that are bigger than before.
That's
and
right.
Therefore they are black, and pretty soon they're going to fall on me, right?
Yes, they have to be big enough to fall and gobble up other ones. They have to be about 28 microns before they can begin to form rain.
But they're already getting dark as they get bigger.
Yeah, that's right. Okay, and if you look at a cloud on 3 o'clock in the afternoon, and when there's lots of sunshine around, they look dazzlingly white when they're fresh and new. Okay, and John Latham knew about all this, and he thought that we could make the clouds whiter by giving them more condensation nuclei. And for this, you need to know that to make a cloud drop, you need to have some high humidity. It has to be slightly over 100% humidity, but you also need a tiny little seed to get it started. Okay, it's called a condensation nucleus. And in the air over land, there's somewhere between 1,000 and 5,000 suitable condensation nuclei in a cubic centimeter of air. So you're breathing these in and out.
Let me see. If I see white clouds, are those things that don't have a seed, or
No.
they all have seeds?
Every cloud drop has to have a seed. Every cloud. And what we want to do is to increase the number of seeds, and for the same amount of water, the drops, there'll be an increase in the number of drops, but the same amount of water.
If you put the seeds, let me see. If you put the seeds up there, whatever these seeds are, there will be something that'll hang on to them, and you will form the drop of a little drop.
If the humidity is slightly above 100%, yes.
So almost always you can count. You just put the seeds up and don't worry about the rest. It'll happen.
That's right. Yeah.
Good. Okay.
Now,
And there's lots of seeds in the atmosphere. There's lots of dust or whatever, cloud condensation, nuclei, bits of clay, bits of surface material, animal matter in the atmosphere as it is. And so what you
equally sufficiently distributed, so we don't, but you're going to put up more. Obviously, you think that you need more. Okay.
over the sea, but over the land, there's lots more condensation nuclei. There's lots of dust. There's lots of bits of clay. So we're talking about these clouds over the sea, where there's not so many. The air is generally a lot cleaner, so there's not so many of these particles, these dusty salt. Salt is a very good condensation.
So you're not going to brighten the clouds over land at all?
No.
We couldn't do that because there's already so many nuclei there. There's between 10 and 100 over most of the sea area, and then 1,000 to 5,000 over the land.
Oh, okay.
So, John Latham thought that we should try adding more condensation nuclei by spraying very small drops of seawater. You need to filter it very carefully and squirt it out, and the salt water would evaporate and it would leave behind a little crystal of salt. All right. And he knew the right sort of size that would be good. And he worked out how much water we'd need to spray to solve the climate problem, and he was amazed at how little it would be, provided the drops were very small. And it worked out about 10 cubic meters of water a second would sort out the problem that we had 20 years ago, maybe a little bit more now.
Now, wait a minute, let me think that through. 10 cubic meters per second, then you've got to spray it from a whole bunch of different nozzles, right, to do that?
We would like to spread it out everywhere evenly. And unfortunately, we'll be doing it with too much in some places and not enough in others. But we'd have to live with that. We would like a nice even distribution, even if it was 10 cubic meters of water a second. If we don't do it right, there'll be too much in some place and not enough in another place.
If you get too much, what goes wrong? What's the problem?
Well, it's just wasting the energy that you needed to put it up. It's not, roughly speaking, every time you double the number, you get about 5% more reflectivity. This was what he found over quite a wide range of conditions.
So you don't want to get too much brightening. Why? What would happen if you overdid it?
In the extreme case, it would make it too cold. We've got a very nice way of adjusting to get it to what we want. But we would like to go back to where we were in perhaps 1920. I don't know, that would be my guess. And we can do this by adjusting how much spray we put up. And if we put up too much, it'll be too cold. So we would put up less.
Okay, now you're going to put this up, and it's going to reflect the sunshine, so it doesn't warm what's underneath. But you're doing this over the ocean. But we live on land, so why?
It's because the wind over the ocean gets cooler, and the wind then blows over land. If you look at the weather forecasts, the temperature depends enormously on which direction the wind is coming from, south winds, north winds. So although we're adjusting the surface temperature of the sea, we're actually affecting how the wind that's blown over the sea will feel like when it comes onto the land.
You've got to think of the atmosphere as a whole system. And the main function of the atmosphere is to take heat from the hot equator to the cold pole. So my argument is, if you want to cool the pole, the easiest way is to reduce the amount of heating at the equator or in the equator regions. And what we have been doing is we've been putting more CO2, methane gases in, which is heated the air over the equator regions. It is also, it's not just CO2 and methane. Many cloud physicists, which I am one, have been saying that we've actually putting all the pollution into the clouds, the work of the big quarrying industries has actually made the clouds darker. So they absorb more heat. And this has never come into the IPCC discussion. We know that increasing the amount of CO2 in the atmosphere increases this greenhouse effect. But if you make the clouds darker, or you remove the clouds, then the planet will warm up. And some cloud physicists have, with good argument, saying we've been making the clouds dimmer. So it's all part of the same issue. If you make the clouds brighter, and the best clouds to try are these layer clouds that you sometimes see, stratocumulus. You sometimes, when it makes an awful day, there's no cumulus, you can't see the sun. Those are the ones that cover a relatively large area. So it's these clouds only that would be most effective to focus on. So if you can get those clouds, and they cover about 5% of the globe, if you can get the oceans, so if you can get those reflecting a little bit more, you've really addressed the problem of the planet heating up. It's not a solution. The solution is to remove the CO2 and methane. But as a temporary fix, you can cool the planet down. You're still going to get acidification of the sea. But it's the role of the clouds. And the final point I'd like to make is when you said I was a modeler. And the problem with the models are they don't really have clouds in them, the climate models. So they cannot assess the importance of the clouds. So every time they improve the models, they suddenly find they're more sensitive to the clouds, which as a scientist, as someone who's measured the clouds knows, it's these clouds that make an incredible difference. And the modelers haven't covered this.
The guys who are most influential in deciding what IPCC really believes in, they're not even taking account of the clouds?
Well, no, this is one of the big battles at IPCC. If you look at the Russian model, they have a thing called climate sensitivity, and they say the planet's only going to warm up by 1.7 degrees, so that scientists from Saudi agree with them, etc. But if you get the higher resolution models like the UK one, which is more accurate, more smaller, like a weather model, they say 5.8 degrees Celsius. So IPC said, oh no, the UK model, and there's a few others, are too sensitive. It's not going to be like that. And the Russian model is 1.7. That's all it's going to warm up by. And I would argue we're already over 1.7 if you look at extremes. So yes, the models, the whole point of it's based on these models that are inaccurate.
That's amazing, because I mean, I was already disenchanted with the IPCC, but you've really wrecked them now, that statement. Now let's go back to something else you said earlier, a minute ago, where, if I'm not mistaken, you said something like increasing the methane warms the temperature at the equator, and then the atmosphere moves it to try to warm the Arctic. Oh my goodness. Now, is that what you said? Because
that's what I said. Yes, it's another gas. But what happens, the signal that all the gases spread out in the atmosphere. So the methane gets produced in Canada or northern Russia or from farms in northern hemisphere. So what happens is the equator regions, subtropical regions we call them, warm up more, and the poles are radiating out to space. So you're going to get more intense hurricanes, for example, because you've got there's a bigger temperature difference between the equator and the pole. And that is why you get more intense hurricanes. You're not getting more hurricanes, but the hurricanes that you're getting are more intense. And this is recognized by the meteorologists. So if you can cool the equator regions more, you reduce the intensity of the hurricanes.
okay, now I've got friends like Peter Wadhams, who's interested in cooling the Arctic, but he's starting at the top of the world. You're trying to start things at the middle.
You can do both.
No.
You can do both. And I would argue
we need to do the Arctic especially important, because it's a very good reflector if it's covered with ice, and it's a very good absorber if there isn't any ice. Okay, so there is a very horrible positive feedback if we lose the ice in the Arctic. Okay, so what we need to do is Arctic and equator.
Yeah. And
we could do the Arctic for just 2 months in the summertime, and then move the vessels that we used to make the spray down to the equator to moderate hurricanes. So we want to be able to move our sources of the extra nuclei around quite quickly.
The problem with that is there isn't very much ocean over the Arctic. And that is, I mean, I agree with Stephen totally. It's just, we have to work out where the optimum place is to make the clouds brighter are, because the clouds have to be there, the sun has to be out. But I would argue for much of the year, obviously for half the year, the Arctic's dark, so there's no point in doing anything there. But for much of the year, cooling these clouds, I like these layer clouds, these stratus clouds near the equator, is the most cost effective if you're in a hurry. But I keep emphasizing that if you look at the southern Andes, there's been a lot of smelters down there, copper smelters, and they have actually made the clouds there dimmer. They've dispersed them because they've thrown so many particles up of the wrong size. So I think there's a lot of cloud physicists who would argue that this has not been included in the IPCC discussion. We're actually making the clouds dimmer. We've been interfering already.
What about the Antarctic? Maybe the air is clean enough over the Antarctic too, so that there's adding particles, spray water or something to the Antarctic would also brighten the clouds there. And at that time of year, maybe that would do some good.
Could easily do that. At the moment, the Antarctic melting is because of having warm water quite down deep, which is undercutting the ice that's out over the sea. And that's why the glaciers are breaking off. And so what we would want to do to save the ice in the Antarctic would be to find out where the water is coming from. It may be somewhere up in the Indian Ocean, wherever there's a lot of heat going into the water. Now that is making it a bit heavier because it's evaporating the water and leaving the salt behind. So that's why that water is heavy and can go down deep and get under the ice in the Antarctic. It's a complicated network of currents of water that's going from higher latitudes down to the, from lower latitudes down to the Antarctic. If we knew where they were, we could make our spray vessels concentrate in those areas.
Yeah.
So you don't know where the ocean currents are going?
Well, we do know where they are, but it's complicated, and we might change them if we change the water temperatures. So
the warm water from in the southern hemisphere, from the subtropics again,
it's also
goes down towards the Antarctic and melts the ice. But it's slightly complicated.
Is that the Humboldt current?
That's one of them is bringing back from the Antarctic.
Okay,
but
go on.
Where there's a Humboldt current flowing north, there'll be some other bit of water flowing south.
So it's a huge circulation pattern but in a warmer climate, it gets complicated because you get more snow falling over the Antarctic. But so you get, because it's wetter, but the northern hemisphere is the one where with the oceans that you really see the most, you get a different circulation pattern. And this is related to something called the jet stream. And if you look at the Weather Channel, you'll see the jet stream. And sometimes they talk about meanders. You talk about snow in Florida. So when you get snow, you get this northerly airstream coming down, producing snow in Florida, which they never have. But you get the opposite. You get then the air going up over the eastern seaboard of the US, all the way up to Greenland and melting the ice in Greenland. And Greenland is covered with snow and ice, partly because it's so high. So if you melt the water over the ice over Greenland, you're not likely to get it back very easily. It's different in the northern hemisphere and the southern hemisphere. But yes, these Antarctic icebergs that are breaking off at increasingly alarming rate are actually melting and going into the southern Atlantic and the southern Pacific.
That you know more about the North Pole than you do about the South Pole. Is that, it doesn't sound like you've got a good plan yet for what to do about the Antarctic.
Well, no, because yes, we have, because if you cool the water, reduce the heat at the equator, you will, in fact, promote ice at both poles. So it's not specifically in the summer. Yes, it might be an advantage to seed there, but you're going to get maximum benefit by cooling the subtropics. And if you look at the southern hemisphere, the winds blow round and round and round. They don't have these meandering jet streams. So they don't have this sudden problem of melting huge chunks of Greenland, because the jet stream just goes round and round. It doesn't do what we have in the Northern Hemisphere. It's all connected. You change the amount the equator warms up, and you change the circulation in the Northern Hemisphere especially.
So you're in favor of putting all of these cloud spraying devices around the equator in the ocean?
Well, I prefer that.
To have them. That may vary through the year.
Yeah, but
Sorry,
obviously,
David, I didn't hear what you said. Say it again.
You'd put the spray vessels where you decide to have them to get the best use, and this will very likely vary with the seasons. You might want to move them north in the May, June, July, and then south in November, December, January, and we'll have to learn where to put them to get the best advantage. But fortunately, when they're not spraying, they can move very, very fast, and we can get them from the northern hemisphere to the southern hemisphere in about 3 weeks, so that we can use them as a very flexible tool. And as we learn more and more about how to use them, we'll be able to do a better job.
Well, if you were to try to spray, which it sounds like you're not planning to do, but if you were to try to spray over Antarctica, you couldn't do it with your ships, right? Because your ships are in the water and Antarctica's all ice.
Well, but the wind can blow, so you'd be cooling the air around the Antarctica.
You would be. So it's just as good, maybe, to spray around the periphery of Antarctica.
I like to think of it as having a sunshade. So you get it's hottest when the sun is overhead. Mm-hmm. So why not move? If you have your sunshade vertically over between you and the sun, then you get maximum cooling. So obviously in the summer, you'd probably want to go to the cloud decks towards the northern hemisphere. And then in the winter, you want to move them to the southern hemisphere.
Okay, now you said something else back there that puzzled me when you said it was methane that warms the equator area. Methane doesn't concentrate in the equator, does it? Or is it methane is a worse warmer and therefore, well, I don't know. Explain a little bit why the methane is relevant to explaining the heating of the equator.
The methane is like carbon dioxide, but it's about 20 times more efficient at warming the atmosphere up.
Objection. It's 20 times more efficient if you run it over 100 years.
That's right.
In the first year, it's about 200 times worse than CO2. And it's the first year that we're worried about if there's a big release from the permafrost. But it's nearly 200 times worse in the first year. Mm-hmm. And there's an awful lot of methane stuck underground, which would come out, and is already coming out in Siberia, and in enormous amounts.
If you could get rid of the methane, that's as good as brightening the clouds, isn't it?
Yes.
Okay. Well, I've interviewed
you can brighten the clouds to stop releasing the methane.
Stop producing or take it out of the ambient air. And this is a distraction. I don't want to dwell on this, but I did interview two guys who are planning to put they have a pilot project they're trying to get going that would actually use iron salt aerosol to combine with the methane and reduce it to CO2 plus, I don't know, whatever's left over, but water. Water. Yeah. So then if you did that on a good scale, that could help too. I don't know what kind of.
It would be very good indeed. We need every tool we can. Uh-huh. That's an excellent one.
Can I add though that water vapor is the biggest greenhouse warming gas. So as you increase the amount of water vapor in the atmosphere, then you actually make the planet warmer because you get feedback. So they work out that for every degree Celsius or 2 degrees Fahrenheit, there's a 7% increase in water vapor. So idea that we can let it continue is completely fallacious, because the more the planet warms up, the faster the rate of warming will go. So if you increase the planet by 4 degrees Celsius, or I don't know, 8 degrees Fahrenheit, 7 degrees Fahrenheit, you have a huge problem, because the water vapor dominates the heating effect. So the whole thing becomes cyclical. Now, the advantage
Just
of
a
water
minute.
vapor,
I can't, my mind just boggled. Okay. So why are you guys going to spray water into the atmosphere and create more water vapor and think that's going to help?
we're
We're
not.
really spraying salt crystals into the atmosphere. The amount of water we're putting up is really tiny, tiny. If we make the sea a bit cooler because we stop the sun getting at it, that will stop its evaporation, and so there'll be less water in the atmosphere over the sea. But it's really the salt crystals that we're doing. The amount of water we're putting up, 10 cubic meters a second, compared with the amount of water in the atmosphere already, is just nothing at all. It's the nuclei that we're trying to get.
It's the salt crystals, the cloud condensation nuclei that we're putting in, and we're just the idea is just to make the clouds brighter.
Yeah.
Think of your sunshade umbrella. We're just providing a temporary fix to this. And the advantage is, if there's anything goes wrong, if you switch off the sprayers, within 2 weeks, the atmosphere returns to the state it was before.
And I said something about spraying iron salt aerosol. It's going to make CO2 plus water. Now, did you object to that because it's going to create more water vapor, and therefore it would have a negative side effect?
No, the amount of water vapors it makes is very, very small compared with what's already there.
So you don't foresee any downside to that problem. Okay. Okay, go on. You've got me convinced we're okay. Now, please, let's figure out what to do. How do we get there? My problem, as I choose my problem, is to figure out how to get people to listen to you and do what you say. And I don't understand why we just had this huge conference at Glasgow and not a word about what you're suggesting.
Right. The problem is that the politicians think that getting to zero emissions is enough, and it isn't nearly enough. We have to actually go in the other direction. At the moment, the things are really unacceptable in lots of places in the world, but they're going to be far worse if we go on emitting CO2 and tapering it down. By 2050, it'll be maybe twice as much as we've got in the atmosphere now. You need to get the emissions stopped, but you also have to get rid of the CO2 that's in the atmosphere, which you can do in various ways. One way to do this is to grow more vegetation, and you can do it. Trees, it's a bit slow, but I think they need 20 or 30 years before they're operating. But the one thing that looks very attractive is increasing the amount of phytoplankton in the ocean. They absorb a very large amount of CO2, and they do it very quickly, in just a few days. And you might be able to do this by increasing the number of nutrients that the phytoplankton need to grow. And one of them is iron. And so there might be ways in which you can increase the iron in the ocean and make the phytoplankton grow more and absorb more CO2. This gets gobbled up by zooplankton, and when they die, they sink down to the bottom of the sea and save the carbon down on the seabed. So that's
there is another way, and that is to increase the amount of wetlands. Wetlands that's bordering on the side of the oceans, on lakes, absorb a lot of carbon dioxide. If you start draining them, as we have done, you release a lot of methane. And the wetlands are the most efficient. I would probably argue, but we're only arguing about numbers here, that reintroducing wetlands and bogs is more efficient at absorbing CO2 than planting trees. it's more efficient because it acts more rapidly. In the long term, yes, trees, but in the short term, we're busy draining. In the UK, we've drained so many wetlands, so many upper areas, and that also increases flooding because the water flows down. The same in Colorado. You drain the fields and you reduce the wetlands and you stop the ability, because of turning these wetlands into peat bogs, which is a huge sink of carbon dioxide.
So listen, now I really want to believe you, but what I interviewed a guy a week, maybe 10 days ago, about peat and wetlands. His book is called something of the swamps, Save the Swamps or something.
Yeah.
And as I understand it, they've already, those peat bogs have already absorbed the CO2. And if you drain them, you release it, or you burn, you use
exactly,
etc.
Exactly.
But I don't think they are continuing to continuously absorb more CO2. On the contrary, so far as I know, and he didn't really go into this enough, and I should have asked him, that wetlands are a source of methane, because these rice paddies and stuff are the main place, one of the big places where methane is being produced. So it's a bad thing. Wetlands have this bad side, as well as the good side is they contain enormous amounts, huge amounts of CO2 or carbon in general.
But if you drain them, which is what we're doing,
we don't want to drain them. I agree.
Well,
everybody would say don't drain them.
Well,
but
you are releasing.
If we increase the wetlands, by increasing the wetlands, I don't think you're going to add to the sequestration.
Well, some people would argue we are.
Okay.
Some people.
I need to find that out. How do we solve that question? Because that's really important.
There are some papers that have been produced on this, and I went to a talk a week ago on this very topic, and they said that the wetlands will continue to absorb lots of CO2 as they have done in history. It's like growing trees, but removing them is catastrophic for both flooding downstream and CO2.
But methane is produced by wetlands.
No, it's produced by farming and rice paddies and agriculture. So
in wetlands in general, old regular swamps that were in nature before agriculture.
That's
those
right.
Were not producing methane. Why not?
What grew gets submerged in water and doesn't get released into the atmosphere. And the longer it's been there, the deeper it is. So there's more and more and more carbon as the peat bog gets deeper.
So you're producing coal and peat. So you're continually absorbing. That's where coal and peat come from. The absorption of CO2. Now it's a tight balance, and if you start making rice paddies or you're growing plants in these water-based, you are producing methane in huge quantities. But if you let them just live there, they are absorbing. It's very similar to the fish in the sea. The fish are eating the plankton. The fish die and move to the bottom, and you get oil. So the fish are eating the plankton all the time, dying and producing this layer, which is absorbed. So that is what we're burning at the moment. We're burning coal, which came from the wetlands, which came from peat. It's just a bit older. So there's this continual sink of carbon.
Okay, let me go back to something that Stephen said about phytoplankton. Yes, it would be great to have more phytoplankton, which would create more zooplankton, which would drop to the bottom of the ocean and sequester things. That's what we've heard. That's what some people tell me. And iron filings would do it, but fertilizer will do it too. And I have another friend who's worried, in fact, two of them, a guy named Peter Ward and another guy named Paul Werbos. And those two people are concerned about extinction events, which they say most of these extinction events or some of them anyway, I don't know which ones, have occurred as a result of the emission of huge quantities of hydrogen sulfide from the ocean. And this happens because you have these dead things falling to the bottom of the ocean, and there are bacteria or archaea at the bottom of the ocean who don't like or don't have oxygen there, and they gobble up these things that are falling down there, and they make hydrogen sulfide, which kills us all, and as well as every living thing on the planet, which is not a nice thing to do.
It has happened before, yeah.
So we've got this contradiction. Do I want these phytoplankton to multiply, or do I want to get rid of them?
Well, what you need is to make sure there's oxygen at the bottom of the sea. If you have oxygen, you won't get hydrogen sulfide. So it's the stratification of the ocean that is causing the sulfur dioxide.
How do we get the bottom of the ocean oxygenated then?
But there is another complication to the ocean. There's a thing called the Gulf Stream, which keeps a lot of the northern hemisphere and Europe warm. But there's something called the Atlantic Meridional Overturning Circulation. And that is a circulation which it takes CO2 into the cold waters off Greenland and takes it all the way down to the Antarctic, and it comes back up again with the Gulf Stream. Now, about 8,000 years ago, there was a Younger Dryas phenomena where this overturning circulation stopped. And this was caused by massive melting of North American ice. Now, the IPCC said that this would not stop in the next 100 years. It's very unlikely.
What wouldn't stop?
This circulation,
AMOC.
this OEMOC, this meridional, this circulation. But if it does stop, and some other people, scientists, meteorologists, oceanographers say it could stop, in which case you'd have a huge impact on the northern hemisphere. Mm-hmm. Why would it stop? Because you're releasing all this cold water from the Arctic pole. It will stop. It's not the Gulf Stream, but it will stop the effect of the Gulf Stream. So areas like Newfoundland, Scotland would cool down by 5 degrees Celsius, 9 degrees Fahrenheit, and cause lots of storms. So there is a possibility that this global warming, in melting so much Arctic ice, will stop this overturning circulation. And the IPCC dismissed it as likely to occur. Mm-hmm. But other people are saying, paleontologists, oceanographers are saying, this has already reduced by 15%. So the picture is not clear what could happen. If we continue to melt the Arctic ice without stopping it with marine cloud brightening, then the impact could be this circulation would switch off. And Maine, New England would cool down by several degrees Celsius. Scotland would certainly be a lot colder.
Yeah, one of the things Peter Wadham says is he refers to something he calls chimneys, that there's a certain place where the water goes down and makes
exactly
it loop to go.
Circulation.
Yeah.
Yes.
Okay.
That's part of it.
So he said that they can't find this chimney anymore, or there's something, they need to have some expeditions to locate this chimney, because if it goes wrong, that is that connected to this?
Yes.
This is exactly the same thing. Exactly the same thing. Yeah.
Okay. So what we need is some sort of big alarm bell. Because, what you're pointing at, all of these things are so troubling and all of them are so interconnected that the idea that we have meetings and people don't even talk about them, and that the public is completely unaware of them, that makes me think this is, if I'm here at this microphone to do anything, it should be to try to make people think about this and take it seriously. I mean, because it may be baloney, but if it's not baloney, you can't fool around with it, right?
That's right. I think on a scale of 10, COVID is about 1 to 2 in severity and the impact on lives. And this global warming is a 9 to 10, because if it happens, you're going to get millions and millions of people in Bangladesh, all the low-lying islands. You're going to reduce food production by 30%. I'm not sure what it will do to the northern USA wheat production, because that would be severely impacted. So you've got food production in places like Ukraine being affected, huge breadbasket of Europe. So I think it's the politicians do not want to accept that there is a possibility that these things could happen.
Listen,
it's like
I read the Globe and Mail, and today's news front page is all covered with information about floods in British Columbia, which have
exactly
out. British Columbia produces something like 25% of the food that, and I don't know for all of Canada or what, but it's a huge amount of the food, and that's going to be destroyed. There are trillions, or at least many billions and billions of dollars worth of crops and agriculture that have been destroyed just by these floods, not to mention the fires that preceded them, and the mudslides and the heat dome and the whole thing. So it's not a future thing. It's food shortage should begin this summer, this summer.
Within 5 years, there will be major food shortages. It has to be, because when people say 1.5 degrees warming, that is irrelevant. What is most important to me is the extremes. And when NOAA says the Northern Hemisphere was 2.8 degrees warmer this July, 2.8, not 1.5, and that's where the extremes are, that is going to have a huge impact on food production. And it's not just the temperature, it's flooding and those things. We have 5 years, I think, before the impact is really felt.
Okay, now what do we do? Where do we go from here? What could make a difference if Glasgow's COP meeting didn't do anything that you need to see done? What do we do next? Tell me, and I'll work on it.
Well, we need to design. We need to finish the design work. It's quite well advanced of the ships that we can use for making the spray. We need to understand where and when we should use them to best effect, and also where we shouldn't use them if it's going to work in the wrong direction. And in parallel with that, I would like to see ocean iron increasing, and there are lots of ways in which we could use more vegetation to soak up the CO2.
Yeah. Well, this is where Stephen and I slightly disagree. We could do the science within 5 years. I think we could produce a system that would cool the planet down. The biggest problem is the politicians and the governments. How do you get through to them? Most of them are only there for 5 years. How do you get them to realize? They get persuaded by COP26. There were more people from the fossil fuel industry at COP26 in Glasgow than for 10 or 20 nations. There's a huge political blockage. And I don't know how we get around that. We had the ex-government scientists for the UK not allowed to talk about, couldn't get a slot at COP26 about marine cloud brightening.
They couldn't get a slot. Tell me why.
Right.
How did that's because the thing that not being a scientist, all I can say is I might be able to call somebody in government, but if you're prohibiting scientists from providing information that some other people don't want to hear, we have to do something about that.
Well, it's the UN that controls this. So the United Nations is this conglomeration. So when you produce a report, it has to satisfy everyone. So without being blunt, it has to satisfy the Russians, it has to satisfy the Saudis, the Indians, and the Chinese, because a report will not come out unless they all agree. And there's the car industry, huge vested interests, and the politicians, to my mind, are just not in control. It's big business. And until what I would do if I was in charge, I would approach the insurance companies, the reinsurance. That's how you got the sprinkler system in New York. At the turn of the last century, New York Senate wanted to put sprinklers in. It couldn't get passed. There was one fire in one building, in New York, wooden building. The insurance industry said, right, you've got to all have sprinklers. So the New York Senate was still fighting and arguing over this. And in effect, to get the building insured, you had to have sprinklers. And that was a classic case of where the insurance industry said, we're not going to insure you anymore unless you have sprinklers.
Thank you.
So I think that is go to Willis Ray or some of the big insurance companies. That was what I would do.
Okay, that's something I can do.
Because they will have to underwrite the floods, they will have to underwrite the loss of crops.
Right.
But how you get through to them, I have no idea. They supported my studies. They supported my work with letters only because they wanted to know what I was predicting with regards to floods and temperature. And I've sent them the papers and they know. But if they have bigger and bigger losses, they're going to get worried and they can put pressure on. That's the only hope I've got.
What they will do is not accept applications for insurance. They'll say, right, you're not insured anymore. What they want to do is to have some accidents so people know they need to get insurance, but ones that they can predict the cost of and charge the premiums, which are a little bit more than that. So they want some accidents, but not too many, and they want them to be able to predict the cost of its.
Yeah, I went to a daycare centre in Boston, and there's a new daycare centre, and there were huge retention ponds where stormwater could rest, and 2/3 of the land was covered by these dips, where when you get a heavy rainstorm, it will go into the retention ponds. And this was required by the insurance companies. This was in North Conway, White Mountains. And it's staggering. Over the last 10 years, the insurance companies have insisted that if you want flooding insurance, you've got to build retention ponds. I don't know what they do about crops, but flooding is another issue.
I don't know anybody in the insurance business personally, but it isn't that hard for me to imagine how to get people to have a conversation with some insurance executives so that if you present the risks and for example, on LinkedIn, there's something called risk management. There's a social group called risk management. Well, okay, they've 30,000 or 50 or 100,000 members or something like that on LinkedIn. So you present something saying the risk, you need to know about the risk of these threats, and you're not being told. So let's work on getting to those particular people, because now, tell me, for example, what happened? I don't think you know, but let me imagine when people began to realize that tobacco was really killing people. Did the insurance companies react by taking seriously this information and warning, or maybe changing the rates for insurance for smokers or something like that? Did they do that? I don't know.
They definitely asked if people were smokers when they were setting up life insurance.
Mm-hmm. Well,
they never used to ask that. They never used to ask it. And if you were 65 and you were a smoker, then it was in the UK, I had a friend, and it was very difficult to get insurance. That's just a consequence. But you're talking here about governments, and the trouble with it's flooding you can cope with, but not droughts, because you're going to get. It was amazing because my studies I thought were wrong. My studies, modeling studies, said Arizona, the whole west coast of the USA was going to reduce its precipitation by 10-20%, and you're going to get droughts. And suddenly, I don't believe these models really, but suddenly you've seen over the last 2 or 3 years, the number of fires, the number of droughts, the Hoover Dam is now dry. This will continue. If you believe my modeling results, which I'm worried about because I don't believe in models, then it gives you this very, very clear signal. And one of the biggest signals in the world is the West USA. Down the West Coast, down the Andes, British Columbia, all the way down to California, down to Arizona, New Mexico. And the results indicate that.
You guys have just given me a handle, because I'm going to be, for my next issue of Peace Magazine, I'm going to write a piece about all of these terrific threats, that how they're interacted, the stuff we've talked about today mostly, and I need to put it out to the people who read my magazine and that have the website, and I will be publicizing it. But the angle there of saying we need to think about our contacts with people in the insurance and risk management business, because those are the people who might listen to people who are not being heard otherwise. Fair enough?
I think that's exactly right. And it's the same problem. We had a huge blocking structure heat wave over Northern Europe, and Germany got flooded and the floods. Now you've got an example of British Columbia being flooded, and you've also got this heat wave. I don't like the word heat dome because you've got cold domes, but you had this heat dome, or whatever you want to call it, and these floods going around the outside, and it's the same meteorology. It's the same dynamics. It's the same activity. You can't separate one from the other. You get one and you'll have the other together.
All right,
and
got it.
They're associated. The drought in the West Coast, and you get the British Columbia floods. It's all connected.
Thank you so much. This is that you've given me my assignment for the next week, write this article. And I thank you very, very much. Now our time is up. So I'll get back to you, because
thank you very much.
You're very, very important people in this world. So keep up what you're doing. Bless your hearts. Thanks.
Thank you very much.
Bye.
Pleasure. Bye. Bye.